Hi everyone, today I will talk about the significance of the speed of light, a key constant in physics. The speed of light in vacuum is 299,792,458 meters per second. In electromagnetism, it connects electricity, magnetism, and light. In relativity, Einstein showed the fastest speed possible, leading to E equals to mc squared with linked energy and mass. In cosmology, it used to measure distant light year, helping us understand the size of the universe. And finally, in measurements, it used to define the meter itself.
Ole Romer in 1676 observed that the timing of Jupiter's moon eclipse was delayed when Earth was farther from Jupiter and earlier when closer. This delay was because light takes time to travel. He concluded that the light travels at a finite speed and estimated to be 220,000 km per second. Later on, Armand Fizeau and Foucault used a rotating toothed wheel and a light beam reflector of a distant mirror. By adjusting the wheel speed to the block of returning light, Fizeau calculated the speed of the light to be 313,000 km per second, and Foucault improved the experiment and got 298,000 km per second. Albert Michelson in 20th century used the modern technique called interferometer with multiple mirrors to measure light's travel time over long distances. His highly precise experiment gave the modern value of light speed, 299,796,000 meters per second. Another method is time of flight method. This measures the speed of light by timing how long it takes for light to travel in a certain distance.
Alright, so now I'm going to present about a challenge in approaching speed of light in particle acceleration experiment. As we all know, in this experiment, you consume enormous amount of energy to accelerate the particles in approaching speed of light. As particle approach the speed of light, the mass will increase due to the principle of special relativity according to Einstein theory, and the formula will be E equals to gamma mc squared. Energy required to accelerate the particle increases disproportionately as their velocity gets closer to the speed of light. Energy requirement will become astronomical and infinite height. Besides that, the next challenge and the significant obstacle will be the material and infrastructure limits, as superconducting material used in the accelerator have critical field limits. Repeated cycles of high magnetic fields will degrade the material of the wall of accelerator over time. Therefore, more advanced material is required in the future. For example, a high-temperature superconductor is required to operate at less extreme cryogenic temperatures and also higher magnetic fields. Last but not least, the radiation-hardened materials is needed to improve the resistance of radiation damage for longer operation times.
Have you ever wondered what happens when tiny particles speed up really fast? Imagine a particle zooming through space super fast. Now, what if we throw a powerful magnet into its path? Here what's happened. As this tiny particle speeds around the magnet, it doesn't go straight anymore. Instead, it starts to bend around the magnet. But there's more. As it bends, it loses some of its energy by giving off light. This light is known as synchrotron radiation. Now, losing energy in the form of light slows the particle down a bit. To keep the particle moving fast, we need to supply the particles more energy. But here's the tricky part. The faster you want the particle to go, especially when our topic is about approaching to the speed of light, the more energy it needs, the more energy it loses, and the harder for it to speed up. So speeding up particle is nearly impossible when we talk about the condition is near the speed of light because of its energy loss and the amount of energy needed to speed it back.